Hello.
Yes, sir.
Just a minute. So we just started looking at this tutorial number 5, and in the last tutorial we said that we will discuss it later because that part we have not yet done, isn't it? Okay, so let me just open. This is the problem number 1 which we have seen in the last class. Is it the problem number 1? No, I don't think. Let me just open that. So is it visible? Did I share my whiteboard? No. Okay. Let me just share the whiteboard. Is the whiteboard visible to everyone?
Yes, sir.
Yes, sir.
Okay. Let me just. Okay. So this is the problem. I think some initial discussion we had in the last class, but again, I think you'll appreciate that discussion now uh, in a much better way compared to what we had earlier. Okay. So before we start the tutorial, again, I have corrected all your queries regarding your examination. Also, some problem happened, so that also got corrected. So I guess you can check your marks on Moodle, isn't it? So all the queries and everything is resolved. Uh, okay, so let us start with the tutorial question. Did I started? Yes. Okay. Okay, so what is been given in this problem is a mercury purified by distillation is cooled by passing it through a double pipe heat exchanger. The inner tube uh, internal ID is given, that is 13.5 mm. Whereas the thickness of this inner tube is also given 2.75, and in addition to that, what is given is the outer pipe uh, diameter is also given. Okay, so the question asked here is okay, so the inner tube of the exchanger carries mercury flowing at a rate of 1500 kg per hour, entering at 250 degrees Celsius and leaving at 40 degrees Celsius. Cooling water enters at outer pipe at 26 degrees Celsius and leaves at 40 degrees Celsius. Calculate the required length of the tube. The following physical property values of mercury at the average temperature may be used. So different values of mercury as well as that for water is given here. So remember in the last tutorial also we have discussed here. If you look at the problem statement itself, what is been given is the hot fluid is entering at 250 degrees Celsius and leaving at 40 degrees Celsius. Okay, and at the same time the cold fluid is entering at 26 degrees Celsius and leaves at 40 degrees Celsius. So that means outlet temperature of the cold fluid and the outlet temperature of the hot fluid both is same. Can I have this type of temperatures when I'm using the co-current flow? What do you say?
No, so it should have opposite
It is
direction.
not possible. It is not possible because this outer temperature is outlet temperature for cold and the hot fluid both are same. So even though that part is not been given in the problem, but just by looking at this temperature itself, you can conclude that The only contacting pattern possible in this case is a counter current flow. Yes or no? Isn't it? So that's why I have taken this counter current contacting. So here you can see that the mercury at 2250 degrees Celsius is entering at this end 1 and coming out at end 2 here. Let's say maybe I'll just okay. All right. So now in this case, one more thing is one has to look at. So mercury is flowing through the inner tube, whereas the water is flowing through the annular space. Okay. And what we are interested in, we are interested to find out how much length of the double pipe heat exchanger is required. That is what the question is. If you look at calculate the required length of the tube. Okay. Correct. So these temperatures are given. These different values are given. Depending on that, first we have to calculate what will be the heat transfer area required, and based on the heat transfer area, then we can find out what will be the length of the tube required, because the heat transfer area will be what? This surrounding area around this inner pipe, isn't it? That is what nothing but the heat transfer area. Correct. So if we know the heat transfer area, then we can calculate the length of the pipe. Okay. All right. Again, in the last tutorial, towards the end of the last tutorial, we have discussed that there are 3 types of terms we will have. One is the sensible heat lost by the hot fluid along the length. That should be equal to the sensible heat gained by the cold fluid, isn't it? And there is a third term, how much heat transfer taking place between cold and hot fluid. And all these 3 terms should be equal. Do you all agree with me? Yes or no? So how much heat is lost by the mercury from end 1 to end 2? That should be the same as how much heat gained by the water from end 2 to end 1. And again, that should be the same as amount of heat transferred between cold and the hot fluid. Do you all agree with me?
Yes, sir.
So that is what we have written here. You can see the amount of heat lost by the cold fluid is MHCpH THI minus TH2, TH1 minus TH2, and the amount of sensible heat gained by the cold fluid will be MCCpC TC2 minus TC1. And both these should be same as what? The heat transfer between hot and cold fluid. And heat transfer between hot and cold fluid again will be obtained by using this expression UA delta T LMTD. Why we are using LMTD here? Because the change in the temperature, the driving force which is present at the end 2 and at end 1, these are varying across the length of the pipe, isn't it? So at this end, if you look at the end 2, the driving force is what? Driving force is 40 minus 26. Whereas what is the driving force at end 1? 250 minus 40, isn't it? So that driving force is varying as we are moving from end 1 to end 2. It's not constant. It's not same. That's why we have to use log mean temperature difference. Can you see the point? Does it make sense to everyone? At least problem is clear to everyone what we are trying to say here.
Yes, sir.
Yes.
Okay. So now let us, try to solve this problem one by one. So let's look at the sensible heat lost by the hot fluid. Why we are looking at the hot fluid? Because for a hot fluid, inlet temperature as well as outlet temperature both are given, isn't it? Inlet temperature, here you can see inlet temperature is 250, outlet temperature is 40, and also the mass flow rate is given. Correct. So we will start with this. For a cold fluid, only the inlet temperature and the outlet temperature is given. But what is the mass flow rate? That is not been given. How much is the flow rate of the water flowing through this annular region? That is not been given. Yes or no? So we will start with this. But before that, let's look at the cross-sectional area of the inner tube. What will be the cross-sectional area of the inner tube? So cross-sectional area of the inner tube, if we calculate, that is, let's say, it will be A1. So A1 will be given by what? Inner tube is the tube from which the mercury is flowing. So what is the inside diameter of the inner tube is given? 13 mm, isn't it? Yes or no? So this area will be pi by 4, 0.0135, 13.5 mm is given. So square. This will be the area. Do you all agree? Hello?
Yes, sir.
So what is the value? Can anybody calculate? What is the value? You should get 1.43 10 raised to power minus 4 meter square. This is what you are expected to get. Now cross sectional area of the annular region. Annular region, what will be the cross sectional area? So area of the outer pipe minus outside area of the inner pipe. So what is the area of the outer pipe? Pi by 4. Outside outer pipe, what is the diameter? Diameter given for the outside pipe is, if I am not wrong somewhere, .41 mm. 41 mm is given, isn't it? So that will be 0.041 square. That is the area of the outer pipe minus pi by 4 the area of the inner pipe. But area, which area? Outside area of the inner pipe is required. Remember, in this problem, inside diameter of the inner pipe is given, that is 13.5 mm. But also in addition to that, the thickness of the wall is given, isn't it? So if I'm having this pipe, let's say if I draw the complete figure, this is, let's say, outer diameter and this is, let's say, inner diameter. So this is given as 13.5, but this thickness between these two is 2.75 mm. And this diameter is given as 41 mm, isn't it? So what will be this area? Remember, inner diameter is 13.5. What will be the outer diameter? 13.5 plus 2 into 2.75. Do you all agree? That will be the outside diameter of the inner pipe. Outside diameter of inner pipe. Do you all agree or not?
Yes, sir.
Yes, sir.
So this will be 19 mm, isn't it? This will be around 19 mm. So we can write 0.019 square. So what will be this area? This area comes out to be
1.036 into 10 raised to minus 3.
Minus 3 meters. Okay, all right. So these are the two areas which we have obtained. Now what we have to do is we have to make a balance and find out what will be the mass flow rate of the water, because mass flow rate of the water is not been given. Mass flow rate of the mercury is given. So mass flow rate of mercury is given as mass flow rate of the mercury is given as 1500 kg per hour is given, isn't it? Correct. Right. So we can write down this expression. Q is same as one. Okay, maybe I'll just write down that mH CPH TH1 minus TH2, and that should be same as MC CPC Tc2 minus Tc1. Isn't it? Correct. So mh in this case is given as what? 1500. What is the specific heat of the mercury? Specific heat of the mercury is given. If you look at the, okay, so that is given as 0.14 kilojoule per kg into TH1 is 250, isn't it? 250 minus 40, and this should be equals to MC CPC. So MC is unknown. CPC is again specific heat of the water is given as 4.2 something, isn't it? If we are not wrong anywhere. So specific heat of the water is given at 4.2 kilojoule per kg per degree Celsius. So that we can again put it here. So we can write that 4.22, and this temperature difference is what? 40 minus 26, isn't it? So MC comes out to be, anyone?
750
kg per hour. And also you can calculate the value of Q, the amount of heat transfer between cold and the hot fluid, that can be directly given as this MHCPH TH1 minus TH2. So we can calculate this as 1500 into 0.14, 250 minus 40. So this comes out to be, this is kg per hour. This specific heat is kilojoule per kg per degree Celsius. So what you are going to get is Q, you are going to get as, in this case, the Q value which you are going to get will be kilojoule per hour, isn't it? Kilojoule per hour, that is what you are going to get. So this value comes out to be, if I calculate 1500 into 0.14 into 250 minus, so 4400 kilojoule per hour. Is it correct?
Yes, sir.
Yes, sir.
Okay. Now, so far we have looked at the both the terms which we have looked at. We have looked at the how much amount of heat lost by the hot fluid, that we have equated to amount of heat gained by the cold fluid, and based on that we have calculated what will be the mass flow rate of the water, and mass flow rate of the mercury is already given. But what we are interested in, we are interested in finding the heat transfer area. Why we wanted to find out heat transfer area? Because unless we know the heat transfer area in this case will be the area of this entire inside tube, isn't it? Based on that only you can find out the length of the tube required. Correct. So now in order to find out the heat transfer area, what you have to do is, remember the expression is this. If you wanted to find out the heat transfer area, expression is this. Q is given as UI AI delta T LMTD. This is the expression, correct? So first you have to find out UI, you have to find out delta T LMTD. Q you already found out from this, isn't it? Q you already know. Once you find out UI delta T LMTD, you can find out AI, isn't it? And AI, if you know the AI is just pi DIL, isn't it? So L can be directly obtained as AI by pi di, isn't it? So this is what we wanted to do ultimately, correct? But now the question is how we can find out UI, how to find out this. So can you suggest how we can find out UI? Can anybody suggest? Remember, see, is the problem clear to everyone what we are trying to do here?
Yes, sir.
So how we can find out UI now in this case?
So we know thermal conductivity of the wall.
So see, remember in this case, what is the geometry? Geometry is this. This is the geometry. This is the outside pipe, and there is a inside pipe, but with some thickness is there. So maybe I'll just draw even a thickness. Okay, this is what is there. So what will be UI? UI or U naught, depending on, you can have U naught, A naught also here, doesn't matter, isn't it? So UI will be what? 1 by UI will be what? 1 upon HI. Remember what will be HI? HI will be the inside heat transfer coefficient here. Plus DI by D naught 1 by H naught. Do you all agree? Do you all agree with this? Isn't it where H naught will be the heat transfer coefficient here? And since in between there is a metal wall, metal being a very good conductor of heat, we don't have to worry about the resistance offered by the metal wall. So that we have anyway eliminated from here. So 1 by UI will be given as 1 by HI plus DI by D naught 1 by H naught. Do you all agree or not? Does it make sense what I'm saying?
Yes, sir.
So in this case, then once we know that this is how we can find out UI. Now the question is, we don't know what is HI and we don't know what is H naught. This we don't know. Can we find out this? That is the question. Can I find out HI and can I find out H naught? Isn't it? So we can find out HI and H naught by using the correlations. Do you all agree? Do you all agree or not? Hello?
Yes, sir.
So HI and H naught both we can find out using correlations, isn't it? So now what is happening inside this tube? Inside this tube, maybe I just show by a different color. Inside this tube, what is happening? Mercury is flowing. Mercury is flowing. What is mercury? Mercury is a liquid metal. Mercury is a liquid metal, isn't it? Liquid metal. So for liquid metal, we have a correlation. We have a different correlation, isn't it? For a liquid metal, the correlation given here is Nusselt number NUD is given as, if I am not wrong, let me just write down that, is given as 5 plus 0.025 into Peclet number raised to the power 0.8. This is what the correlation is. Correct? Yes or no? This is what the correlation is. So let's try to find out the individual quantities first. And also this H naught is nothing but the flowing of the water through a annular region, but we can consider this annular region. For this annular region, find the equivalent diameter. Find the equivalent diameter. And once we know the equivalent diameter, then we can use the correlation, use the correlations of flow through circular pipe. Yes or no? Do you all agree? Do you all agree or not? Isn't it? So HI I can directly find out using the correlation. So HI there is no problem because mercury is anyway flowing through a circular pipe. So there is no need of finding the equivalent diameter. But water is flowing through a annular region, and annular region is not a circular region, isn't it? So first we have to find out the equivalent diameter for the annular region, and then we have to find out the corresponding correlations and use those correlations to find out HI. So at least background is clear to everyone what we are trying to do and why we are trying to do. Make sense or not? So see, you all have to say something, isn't it? I have done this tutorial several times. It's nothing for me to learn. Okay, it's all for you. Unless you say something is clear, not clear, I will not get to know, because it is kind of, talking to the screen. And unless you say something, I am lost. Okay, so please say.
हाँ सर क्लियर
क्लियर है ना? ठीक है, बोलते रहा करो. अगर बोलोगे नहीं तो मुझे पता कैसे चलेगा कि आई एम whether you are following me or not.
यस सर
Okay, so now at least the background is clear. Now let's try to solve the problem. So we have now got all the ingredients which is required. Okay, all the ingredients which are we need to find out, that we are already aware now. So the first thing here is to find out the, remember in this correlation we have to first find out what is Peclet number. So maybe I will just bifurcate this entire thing. Okay, I will bifurcate this entire thing. So this is inner tube, and this is annular region. Okay, so first thing in the inner tube is we have to first find out the Reynolds number. So Reynolds number, what will be the Reynolds number? dV rho by mu. But V into rho we can represent as a mass flow rate, so that becomes dG by mu, where G will have a unit of what? G will have a unit of kg per meter square second. So that we can directly obtain from what? That we can directly obtain from mass flow rate mh into mh by area. So mh is given as 1500 and it is given as kg per hour. So if I divide by 3600, that is kg per second. Kg per second divided by what is the area of the inner tube? Area of the inner tube is 1.43 into 10 raised to power minus 4. So this mass flow rate in kg per meter square second, this comes out to be check whether this is correct. So Reynolds number in this case, again diameter of the inner tube is given as 0.0135 multiplied by this G is 2914, and the viscosity of the mercury is given. Viscosity of the mercury given in the problem statement is, viscosity of the mercury given is 8.5 into 10 raised to power 8, but that is kinematic viscosity is given, so that you can convert into a viscosity by multiplying the density. So we can write this as 13200 into 8.5 into 10 raised to power minus 8. Do you all agree with me? Hello?
Yes.
So what is the value of Reynolds number? This is what expected.
3.5 into 10 power 4.
35060. Is it correct, this value?
Yes, sir.
Yes, sir.
Now, once we have obtained the Reynolds number, what we have to do is we have to obtain the Peclet number. Now, Peclet number is what? Peclet number is nothing but Reynolds number into Prandtl number. Now, Prandtl number is what? Cp Cp mu by K. And Cp value of the mercury is given. Cp value of the mercury is given 0.14 into 10 power 3. So that is joule per kg. Mu is given as 8.5 into 10 raised to the power minus 8 into 13200. So that is Cp mu by K, and thermal conductivity value is 11.5. So Prandtl number comes out to be, anyone? Prandtl number comes out to be? Are you all getting this Prandtl number? Hello? Is it correct? This Prandtl number?
Yes.
Yes.
Yes, sir.
Yes, sir.
So now with this Prandtl number, then we can calculate the Peclet number. So now Peclet number will be what? So Peclet number anyway is the multiplication, so we can directly use the correlation. So Nusselt number is what? HD by K, and that is given as, for a liquid metal, that is given as 5 plus 0.025 into Peclet number raised to the power 0.8. This is what the correlation is. So H we wanted to calculate. D is the diameter of the inner tube. So that is again diameter of the inner tube is 0.0135. Thermal conductivity of the mercury is given as 11.5, and that should be equals to 5 plus 0.025 into Reynolds number we have obtained. Reynolds number, the Reynolds number which we have written 35060. So 35060 into 0.013 raised to the power 0.8. Raised to the power 0.8. Calculate the value of H. Can you calculate the value of H? Anyone? So if you calculate the value of H, what you are, so this is nothing but what? This is the inner pipe, isn't it? So this will be HI di. So HI comes out to be, in this case, let me write down the final value of HI. Just check whether this is correct or not. So value of HI is 7112.30 watt per meter square degree Celsius. Just check whether this value is correct.
Yes, sir.
Yes, sir.
So this is the value of H we have obtained for the inner pipe. Now the same thing we wanted to do it for the annular region. So for annular region, the additional complication is, first we have to find out the equivalent diameter. So what will be the equivalent diameter? 4 into weighted, area by weighted perimeter. This is what the hydraulic radius is, isn't it? So 4 into hydraulic radius is nothing but the equivalent diameter. So 4 into what is the area of the annular region, that anyway we have calculated earlier. So I will just directly write down 10 raised to the power minus 3. What will be the weighted perimeter? Remember, in case of the heat transfer calculation, only this outside area is important, isn't it? Only this outside area is important. Correct? Not this area. So that will be what? Pi into pi d will be there, but that d will be the outer diameter of the inner tube, isn't it? So that will be given as pi. That will be given as pi into 0.019. Do you all agree? Isn't it? This is the outer diameter of inner tube. Do you all agree?
Yes, sir.
So the equivalent diameter, what you are going to get in this case is the equivalent diameter which you are expected to get is 0.0695 meter. Just check whether you all are getting the same. Are you all getting the same?
Yes, sir.
Now mass flow rate. What will be the mass flow rate? Mass flow rate G2, let's say, in kg per meter square second. So that will be MC divided by area of annular region. Isn't it? And MC we have obtained as 750 divided by the area of the annular region. We already know 1.1.3 1.037 into 10 raised to power minus 3. But in addition to this, we should be dividing by 3600 because the 750 is in kg per hour. So this comes out to be anyone? Anyone? What is the value of mass flow rate here?
So 20.09.
201.
Complete answer I was giving, yes. 20.09. I mean value of G2.
Is it correct? Whatever I have written? 201.
Yes, sir. I got 200.9.
So 201 is we have taken. Now based on this, we can calculate Reynolds number. So Reynolds number in this case again dg by mu, isn't it? What will be d in this case? D will be the equivalent diameter. So equivalent diameter. G will be what? G2. Mu will be what? Mu2. So DE in this case is what? 0.0695 into 201. And what is the viscosity of the water given? Viscosity of the water given in the problem is 7.3 into 10 raised to the power minus 4. This is what is given in the problem. So with this, the Reynolds number comes out to be 19136. Is it correct?
Yes.
Yes, sir.
Yes.
Now this Reynolds number is very, very large compared to 10,000, isn't it? Yes or no? This is 19,000. When Reynolds number is more than 10,000, what type of flow it is? Turbulent flow, isn't it? So basically in the annular region, water is flowing with the turbulent condition, isn't it? So flow condition is a turbulent flow. So for a turbulent flow, which equation is the most appropriate one? For turbulent flow, through circular pipe. Remember, once we have taken the equivalent diameter, now we are only talking about the circular pipe, isn't it? So which equation is important? Which equation one should use? Dittus-Boelter equation, isn't it? So this equation you have to remember. This is a very famous equation. So you are expected to remember this. So Nusselt number is given as 0.023 Reynolds number raised to the power 0.8 into Prandtl number raised to the power. Now heating and cooling, depending on whether you are looking at heating or cooling. In this case, what is happening? Mercury is being cooled, isn't it? But here in this case, the water is being heated. Mercury is being cooled, but the water which is flowing outside, that is being heated. So in this case, 0.4. Is it clear? So now you can put all the values in this equation. So again, Prandtl number you can calculate. So Prandtl number is Cp mu by K. So Cp of the water is given. Cp of the water, what is the value given? Cp of the water? Cp of the water given is 4.2 into 10 raised to power 3 into water viscosity is given 7.3 into 10 raised to the power -4, and K is K value. Okay, Prandtl number directly given in the problem. Okay, so we don't have to calculate. Prandtl number is already given in the problem. So Prandtl number given is 4.9. So Prandtl number is 4.9. So now in this case, we can calculate the Nusselt number. So that is HD by K. That is the Nusselt number. What will be the D in this case?
Effective diameter.
Which diameter?
Equivalent one.
Yeah.
Only calculated.
Will it be a equivalent diameter or will it be a the normal? It will be a equivalent diameter in this case, isn't it? So this will be DE and this will be H0. Okay, and this should be equals to 0.023 RE raised to the power 0.8 into Prandtl number raised to the power 0.4. So we can put all the values here. So H0 remain as it is. D is again we have calculated and that value is 0.615, isn't it? 0.615 divided by the thermal conductivity of the water is what is the value of thermal conductivity? Let me just check. Okay, so thermal conductivity is 0.0615. Thermal conductivity is 0.615 and the equivalent diameter which we have calculated above is 0.0695. Okay, so this is 0.0695 and that is 0.023 Reynolds number value also we have calculated. So that is 19,000 something, 19136, 19136.8 and Prandtl number value is 4.9 raised to the power 0.4. Calculate the value of H0. So what is the value of H0? Anyone?
1024.
Okay. So now we have obtained HI and H0. Now we can calculate 1 by UI. 1 by UI is 1 upon HI plus DI by D0 H0, isn't it? So 1 by HI is, what is the value of HI? 711 2.3 plus DI is what? The inside diameter. Remember here the area, this out overall heat transfer coefficient we are calculating inside the inner tube. So what will be DI? DI will be 0.0135. What will be D naught? D naught will be outside diameter of the inside pipe, isn't it? Inner pipe, outside diameter of the inner pipe. So that is nothing but what? 0.019, isn't it? Correct. And multiplied by 1024. So what is the value of UI? Anyone? Anyone, please? Check whether this is correct. Is it correct? Is it correct, this value?
Yes, sir.
Whether you are calculated or you are just saying. Okay. Okay, all right. So now then, after once we have obtained this, then we have to use this equation. Now Q is given as UI AI delta T LMTD. Okay, now delta T LMTD will be what? Delta T LMTD. What is the temperature difference? If you look at the problem, the two temperature differences are what? So the two temperature differences, you can see that at this end the temperature is 40 minus 26, and at this end number 1 the temperature difference is 250 minus 40. So we can write down that in a log mean temperature difference and we can calculate. So log mean temperature difference can be calculated as delta T1 minus delta T2 divided by ln delta T1 by delta T2. So delta T1 is what? Delta T1 is, let's say if I take the end 1, delta T1 is 250 minus 40, that is delta T1. Delta T2 is what? 40 minus 26, isn't it? 40 minus 26? Yes. Okay. Divided by ln 250 minus 40 divided by 40 minus 26. Calculate the value of delta T LMTD. So you will get 72.4 degrees Celsius. Now you can put it in this equation. Q you are already calculated. If you go back and see the Q value you have already calculated. So Q you have already calculated. So value of Q is, okay, I'll just again. So Q is 44100 kilojoule per hour. Okay, 44100 kilojoule per hour. So I will just write down that. So Q is 44100 . So that will be joule per hour, isn't it? Joule per hour. So that I can convert into joule per second by dividing 3600. And that should be equals to UA delta T LMTD. U I have already obtained. So U is 1198.35. AI and delta LMTD is 72.4. So I can calculate AI. So AI comes out to be, in this case, AI comes out to be 0.1411. This is what you are going to get area. And this AI is equals to what? Pi DIL. And we wanted to calculate L. So that means 0.1411 divided by 3.14 into DI. DI in this case will be inner diameter, so that is 0.0135. So the L comes out to be, the length comes out to be
3.33.
1411, 3.14, 0.0135. So 3.33, yes, 3.3 meters. So this should be the length of the double pipe heat exchanger. Is it clear? So length L should be 3.33 meters. This is the final answer. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay, so we stop here unless you have any question to ask. Do we have any question? So if no question is there, let us stop here and we will continue tomorrow. Okay.